Okay, let's look at this problem. Part A, let V be the unit circle and W the point 2, 3. Prove that V union W is a variety. So V is, so how do I prove something is a variety? To prove X is a variety, need to show that X is the vanishing set of some list of polynomials. And they have to be finite list of polynomials. Okay, so the unit circle is the vanishing set of x squared plus y squared minus 1. W is the point 2, 3. So W is the vanishing set of x minus 2, y minus 3. Note this is the vanishing set of one polynomial, and this is the vanishing set of two polynomials. So both of these are in the plane, K2. So one equation we expect 2 minus 1, two-dimensional ambient space minus one equation is a one-dimensional object, which is the unit circle. With two equations, we expect a zero-dimensional object because 2 minus 2 is 0. Right, so the vertical and the horizontal line intersect at the point 2, 3. Okay, so then the union W is the vanishing set of what polynomials? So my first polynomial is here, comma, so this is f1. And then my second polynomial is here. This is called f2. And that's it. That's the end. If you take a point, why does 2, 3 in here? 2, 3 is an element of this variety. Why? Well, because when we plug in the point 2, 3 for x and y, the 2 makes f1 vanish. So, let's call this p. So then f1 of p is 0 because of this factor. And f2 of p is equal to 0 because of this factor. Now let's take, let's say p was a different thing, like square root of 2 over 2, square root of 2 over 2. Well then, f1 of p is 0, why? Well, okay, I don't need to rewrite it, I already wrote it there. Why is this true for this new p? Now let's get a new p. Well, because this factor will vanish in f1. And why does f2 vanish? Well, because this factor vanishes. So even though this factor is non-zero, this factor is non-zero, the other factor is 0. And that's why it works. Okay, what's part B? Part B. Let U be the line x plus y equals 0. Prove that V intersect U is a variety. Okay, so V is the unit circle, U is the line x plus y equals 0. So then, part B, here's part A. U equals the vanishing set of x plus y. It's one polynomial. Okay, I can sort of visualize it. It looks sort of like that. Okay, because its normal vector is 1, 1. And V intersect U will be a variety. Yeah, it'll be these 2 points. So what is it? So V intersect U is the vanishing set of what polynomials? That's how I prove. To prove that something is a variety, write it as a vanishing set of finitely many polynomials. So which ones? X squared plus y squared minus 1, comma. What's U? X plus y. So now I have 2 polynomials. It's the vanishing set of these 2 polynomials. So both of these polynomials must vanish, and that will give not a circle, not a line, but 2 points. What are those 2 points? Well, it's root 2 over 2 minus root 2 over 2, and the point minus root 2 over 2, root 2 over 2. Okay. C. Prove that the set blah, blah, blah is a variety. Okay. So I know how to define each of these points. So like 1, 1, 1. Let's look at part C. So 1, 1, 1, that's just a point in three-dimensional space. It's the vanishing set of x minus 1, y minus 1, z minus 1 of 3 polynomials. In three-dimensional space, if we require 3 polynomials to be satisfied, to be vanishing, we probably cut out a zero-dimensional object, etc. for the other two. And then unions, so what is it? So if I take 1, 1, 1, what are the other points? 2, 3, 4, negative 5. 2, 3, 4, negative 5, 0, 0. Well, this is equal to the vanishing set of, okay, I'm going to need a lot of polynomials. X minus 1. So let's call this F1, F2, F3. And let's call this G1 be X minus 2. G2 will be Y minus 3. G3 will be Z minus 4. H1 will be X minus 5. H2 will be Y, and H3 will be Z. Okay, 27 polynomials. The Fi, G, J, H, K for all I, J, K running over the set 1, 2, 3. Okay, there we go. So this set of 3 points is the vanishing set of 27 polynomials. It takes 27 polynomials to, well, maybe you could find less. So could we use less polynomials than 27? I will leave that question for you. Perhaps geometrically you can think of something.